Okay, so this is what we have. QV is equal to E. Now we know that this thing Q is the electronic charge. We can keep it Q for now. V is the stopping potential. Vs is equal to the kinetic energy is half mv squared, right? So now let's do it over here. The velocity of electron can be derived from this thing as it's pretty straightforward. You rearrange this equation to qvs. Vs is the stopping potential. Okay, so this thing divided by m is equal to v square. So you square root both sides, so you get the velocity of the electron under this stopping potential is equal to this thing. So this is the velocity of the electron. In same way, you could also write down the momentum of the electron, right? So momentum of the electron can be written as, okay, so we know a relationship for energy and momentum. In fact, really that is the main original equation for kinetic energy, which is p squared by 2m, right? I've shown you last time how this gives you a half mv square, because we know p is m times v and then square divided by 2m. So this just becomes 1m cancels with 1 over here, so this becomes half mv squared, right? So this is the kinetic energy, which is equal to q times vs. And in same way, this gives you the momentum of 2m qvs square root, right? So this is the linear, let me write this, the linear momentum of this electron under a specific stopping potential or stopping voltage, right? Now let's see how does this stopping voltage varies as I increase the frequency. Remember, frequency was in our control. There is a specific frequency that we need to provide to get the photoelectric effect or the emission of the electrons, and that is called the threshold frequency. So let's see how does the stopping voltage behaves as the frequency increases, right? So let's suppose that f naught lies somewhere over here. Okay, so the first thing that you know is that until you reach the until you reach the threshold frequency, you would not need any stopping voltage, right? Because there are electrons to stop, so hence the stopping voltage until f naught is 0. Is that point clear? Let me use a bit. Right, so is that clear why until f naught you would have stopping voltage as 0 as well, right? Because there are no electrons, no emission of electrons happen, so no stopping voltage is required, as you don't have to stop anything now because there is nothing. And as you reach this f naught, the threshold frequency, for every step in frequency, you increase a step in the stopping voltage, right? This is because the electron will now have more kinetic energy, right? So when you reach, as you increase the frequency, the electron gains more and more and more kinetic energy. So you need to do more work in order to stop the electrons. So the stopping potential also has to increase if the frequency is increasing. Again, remember this frequency is related to energy as E is equal to hf if I increase this frequency, this total maximum kinetic energy of the electrons is also increasing. But to stop that, we are doing some work, Q times Vs, and this work done has to be increased. You need to do more work to stop the electrons. So to increase that work done, Vs has to increase. So the stopping potential therefore increases. Is that clear?
Yes, sir.
Okay. Okay. So more electrons. All right. We can also see the effect of intensity. We'll actually come to that in some time. Let's first discuss the emission and absorption line spectrums. Right. We'll start with the continuous spectrum. So let's start discussing line spectra. Okay, so and let's see if I have this over here. Yeah, let's bring this over. Okay, so you can see the first over here. Let me change the color. Let's use blue. Okay, so this one you see over here, this is called the continuous line spectra, or the continuous spectrum. And this is a spectrum that is for white light, right? So whenever you have white light and you pass it through some medium that is going to diffract that light, then what you will get is this V, I, B, G, Y, O, and R, right? These different wavelengths that corresponds to different colors, right? And now this is, if I pass this this white light or any well um, not any. The point is that this white light is monochromatic, which means same wavelengths and speeds. Then the other thing I can do is I can take a light that comes from a any hot gas, right? Or a lamp or anything. Or it could also be a light that is coming from a hydrogen gas, passing through a hydrogen gas. When you do that, you observe this spectrum. So you see only this red, green, blue, and violet, right? You see these lines. And if I take a light and pass it through a cloud of cold gas, right, then I observe this type of spectrum. I see black spots, or you can say dark spots at some points. So you see that and this is known as the absorption spectrum, as the light that passes through a cloud of cold gas absorbs that light as the gas is cold, so it absorbs energy to increase its temperature, right? So you would understand that if you remember your thermodynamics, that the temperature always tries to balance between a hot and cold, and there is no such thing as cold, but really heat that flows. So if something is cold, then heat would flow to that. And so this is the spectrum that you would get. This is known as the hydrogen absorption spectrum. We usually stick to the hydrogen gas when we look at these spectrums, right? And we know that all the elements that we have in the periodic table are the only elements, because you get, for these elements, you get the same line spectra of the light that comes from the distant stars in the universe, right? So the most distant light that is coming to you, you take a spectroscopy and pass it through a spectrometer, and you still get the same spectral lines, right? So is that clear?
Yes, sir.
Okay, so okay, we'll come back to this emission line spectra in a bit. First, let me also explain this the concept of energy levels, and what happens when you absorb energy, what happens to the electron, as in when it absorbs energy or when it releases energy. So what we have is we have a nucleus over here. I'll call it capital N, as in it's the nucleus. And then you have energy levels. Now I'll draw those energy levels as straight lines. So any particle that lies on this line is at some energy. Let's, for example, call it E3. These energies are negative. So I'll for to understand why these are negative, and to make sure that these energies are negative, I'm just going to give them some values. Let's say this is minus 16 minus 60 electron volts, and then as you go higher and higher, the next energy level is really high above the E3 ones, and this is E2, and this is, suppose it is minus 20 electron volts, and then you have another one which is now they get they which is 10, suppose, electron volts. So the first thing that you see is that the energy levels are increasing in this direction if I'm considering the nuclear pull of these energy levels, right? So the nucleus is trying to pull these energy levels, but they are increasing in the direction. Now what we have is, we have on these energy levels, we have particles, electrons, right? Now suppose if I have an electron at this level, let's draw an electron is sitting at this E2. What it can do is it can radiate a photon, emit a photon, which corresponds to the emission spectrum. So it radiates a photon outwards. Once it does that, it is releasing energy. So some energy is being lost from this electron, so it drops to a lower energy level, right? And suppose if I have an electron that is also, again, we'll take an example from an electron that sits on E2. If I supply a photon to this, supply some energy to this electron, suppose this is the photon that I'm giving it, the electron rises to some energy level, because now it has gained more energy, so it is capable of jumping up a state, right? So what we see is that when an electron transits from a higher to lower state, this one, a photon with the energy equal to the energy of the difference between these two. So for example, the question might be that what energy of photon I need to release so that it is capable of making this drop in the energy level, and that energy should be equal to the difference between the two energy levels, right? So because it starts from E2, drops to E3, so whatever the difference is between these two, E3 minus E2, is the energy of this photon, right? E3 minus E2. So it is sometimes called the energy gap between the levels, right? So this thing is sometimes also called the energy gap, right? And the other thing is, as we saw, that when an electron transits from a lower to a higher energy state, what it happens is that it can do that by absorbing a photon with the energy that is again equal to the energy gap. So this photon carries an energy of E1 minus E2, right? So this is the energy of this photon. Again, this is also called the energy gap. So you can see this emission hydrogen spectrum that we have here. So what
Sir,
happens during an emission line spectra? Yeah,
sir, how will it drop from E2 to E3?
from E2 to E3. Okay, so it can drop from E2 to E3 as well by releasing a photon of energy E3 minus E2, or E2 minus E3, right?
Okay.
So so suppose that let's draw one electron over here, and let's show that from, sorry, you were asking from E2 to E3, right? uh Omar, you were asking from E2 to E3.
Yes, sir.
Okay, yeah. We already have that drawn over here, right? So this first electron, it drops to E3 by emitting a photon that carries an energy of the difference between the two energy levels where the drop is happening, right? So it drops from one energy level to another energy level. So the difference between those two energies, the photon must carry that amount of energy, which is released, so it falls to a lower state.
For
Okay,
even a
so
photon will be gained.
or
For even photon would be gained.
for E1. Oh, okay, so to jump to E1 from E2, yeah. So a photon will be absorbed by the electron. So you might throw a light, you will throw photons or shine light or a laser beam at this electron sitting in E2. Given that that beam has an energy that is equal to the difference between the two, the electron will jump up. But if your energy is not equal to this two, the gap between these two, it is less than that, then electron will not jump, no matter for how long you shine that laser onto the electron. It is not going to make the jump because it is not getting enough energy to make that jump up, right? Okay, so uh, when an electron jumps up, we call it an excited state as well, right? And when it falls down, it de-excites, right? So anyways, now during this formation of emission line spectra, you see there are discrete lines of specific colors, right? So red, well, green, blue, and violet, right? These are observed on a black screen. Now, how do we get this emission line spectra? You use a cloud of hot gas. So this is obtained. Let me change the color. By using a cloud of hot gas. It can be sodium, hydrogen, or anything, right? Now, well, the electrons of this hot gas, they exist at a higher energy state due to high temperature. They have more temperature temperature, they have more energy, which means they can live inside a higher energy state, right? So that's why we call them excited states, right? So if you have a higher, let's change the color back. So if the temperature is high, this corresponds to a higher energy state. Is it clear why so? Is it clear why the higher temperature would imply a higher energy state?
Yes, sir.
Okay, so this is what we have right now. These electrons are also going to drop. They're going to drop down to a more stable state. They can remain in this excited state for a very less amount of time. And once, because they're unstable at the higher energy state, because that's not their natural state to be in. So in a very short span of time, they're going to drop back down to a more stable state. And that is done by emitting photons of energy that is equal to, again, the energy gap between the two levels, right? And this is the reason why we see these colors of specific frequencies. A specific frequency corresponds to a specific color, right? Because these colors have different frequencies as they have different wavelengths. What does that mean? Frequency is directly related to energy. So that's why this energy gap or this excited state or de-excited state, it corresponds to these different colors being formed, right? So what we how again how this emission line spectra is formed. This emission line spectra, what you have is you have a light source, right, coming in this direction, and suppose you have a cloud of hot gas, and you need some screen to observe what you get from this thing, right? So when you pass this from a cloud of hot gas, it splits into these specific colors, right? So but I'll just draw these two lines, but it splits into these colors, discrete colors. So you, on this black screen, this screen is black. At one point you will see a completely violet line. So let's try to do that. So here you will see a violet line, then you'll see a blue line, and then a bit further apart from it, you would see a green line, and then finally at one end, you're going to see a red line. Right? These you can say these positions of these particles, or sorry, not particles, these lines is coming from the frequencies that corresponds to these colors, right? Okay, so this is emission line spectra. Emission happened because we passed it through a hot gas. And why? Because the temperature was high, which corresponded to a higher energy state. Now, next we have absorption, right? So we have discussed most of the things, but now let's just see what does it mean for having an absorption line spectra. Okay, so in an absorption line spectra, you again have a light. You throw it this time. You throw it through a cold gas. So this gas is cold. So you throw it through a cooled cloud of gas, and what you see is on your screen, you see some colors being formed, right? The colors are like this. So at some points, so on this black screen, you see these different colors of light being formed, but there are some dark spots in between. So what happens is when this, again, this is white light. So when you're passing or throwing a white light through a cloud of cold gas, the photons that have energies which are equal to the energy gap between the two levels are absorbed by an electron, right? As they jump from a lower energy state to a higher energy state, right? So they absorb that energy. Again, let's come back to this energy level diagram. They take that photon, absorb energy from it. Now they are capable of transiting to a higher energy state. And so that's what they do. So hence photons of only a specific amount of energy, which means a specific amount of frequency, are missing from continuous spectrum. So you can see only those specific frequencies where you have this jump from a lower to higher energy state, those are giving you dark spots, right? So is that clear?
Yes, sir.
Okay, so finally, on this, well, we'll talk a little bit more, but the electrons which go to a higher energy state, jump to a higher energy state, as I mentioned before, they'll eventually drop back down to a lower energy state, which is a stable state for them. How do they do that? They do that by emitting the photon that had the same energy which it initially absorbed to go to the higher energy state, right? Because that energy is the difference between the two energy levels, which does not change, right? The energy levels do not change. So it should release the same photon which it had absorbed to make that transition back to down to the stable state, right? But note that these photons that we're talking about, they're emitted in all directions, right? And what does that mean? That means that the light that you get is of low intensity, right? Because the photons are emitted in all the directions, which basically decreases the strength of the light or colors that you would be seeing, which means that it decreases the intensity of the color and it's then barely visible, which is again responsible for these dark spots or dark lines on the screen for an absorption spectra. Okay, so we have less than 1 minute remaining. Let's continue the next in further class. Again, like I said, I would be